All right, I suppose we have a quorum, so I'm going to get started. Welcome to this lecture. Is this lecture 8, I think? Today we're going to talk about two related developments in the field that sort of occurred as we moved through the 1980s towards the 1990s. And in fact, these two developments are closely coupled because it's progress in the one that helps to unlock progress in the other, as we've seen many times throughout the course. And the two topics I have in mind for today are silicon detectors and precision measurements. Of course, many of the measurements we've discussed in the past have been precision measurements by the standards of their time. But as we start to move into the era of larger and larger colliders and larger experiments, the data sets that we're capable of producing and analyzing get larger and larger. To cite an example, many of the precise measurements of the Z boson and its properties come from the LEP collider, which we'll discuss today. And they are the sample of Z bosons that were produced in order to make those measurements number in the tens of millions. We may have taken order of a million bubble chamber photographs in an experiment in the 60s, but very few of those photographs would have actually contained the particle that we were trying to analyze. Here, as the luminosity of colliders increases, and as the electronic sophistication of the detectors increases, it will really pave the way towards these precision measurements. In fact, much of what we now know about the standard model and much of the ideas that we have about what is and isn't possible for physics beyond the standard model has to do with indirect constraints that come from these types of precision measurements. So this is a topic that we'll return to repeatedly in the later parts of the course. So as is by now traditional, I will start the lecture with a sort of recap of what the evolving standard picture of physics looked like this time in 1983, choosing this year to reflect the discovery of the W and Z particles that really cemented the standard model as our best description of the fundamental rules of matter and forces. So what did a physicist in 1983 think? Largely, it's the same as what we think now. You look at this and compare to our current understanding of the standard model, I would argue that in some ways not that much has changed. The discovery of the J psi, maybe, or the upsilon, perhaps, were really the last great surprises leading up to the standard model. As we move through the decades leading up to the present, 1983, this is a little more than 40 years ago. I was born in 1983 for reference. The character of the science is really changing from massive mega projects to massive mega projects, which largely are going to provide a confirmation, however dramatic and technically challenging it may be to deliver this confirmation, of a picture whose details have largely snapped into place as of 1983. And that picture is the following. There's 3 generations of matter particles. One for the electron, that's one generation for the muon, and the third generation starting from the tau lepton. Each of these leptons has their associated neutrinos, and then there are 2 quark flavors for each, which share these fractional electric charge numbers, which are the same across the 3 generations. The upsilon particle, whose discovery we talked about last time, is correctly interpreted as being the flavorless bound state of 2 bottom quarks, or bottom and an antibottom quark. Maybe you hear the term quarkonia for this type of state, or bottomonium in this case, a strange term. And people basically are certain that there must also be a top quark as well as a tau neutrino. Neither of these have been directly observed. In both cases, that direct observation will have to wait until the 1990s or even the early 2000s in the case of the tau neutrino. But I don't think anyone really had significant doubts, even in 1983, that these particles eventually would be found. And by the end of this lecture, we'll see sort of smoking gun indirect evidence that the tau neutrino exists, and most likely no other neutrinos after it. We'll get back to that towards the end of this lecture. The particles W and Z have been seen in proton-antiproton collisions at CERN, and precision measurements of their properties are going to give us a wealth of information about the Standard Model. And I'll comment on that a little more again towards the end. This picture also, I think, basically cements in place the fact that we expect to discover not just a tau neutrino and a top quark, but also a Higgs boson. The confirmation that the W and Z particles exist, not only are they massive, but they have the mass, which is predicted by the electroweak symmetry breaking theory based on measurements of the weak mixing angle, for example, in neutrino nucleus scattering events. Once we see these particles, I think it's all but certain that there is a Higgs boson. We know something about its mass, and efforts to observe this particle directly will be a main focus of collider physics for the next 30 years after 1983. So all this to just confirm what I said at the beginning of the slide, that this discovery is not unexpected. The discovery of the W and Z is not unexpected, but it does usher in an era where particle physics will largely continue to confirm the details of the Standard Model with few, if any, large surprises. Are there more surprises left for us in store? Maybe, maybe not. We'll talk about that more when we get to the end of the course and talk about future facilities and the direction of this science. So this is a picture of the UA2 experiment, one of the two large experiments that participated in the discovery of the W and Z particles. I think when we first presented it in the last lecture, we drew a contrast between UA2 and its sister experiment, UA1. Compared to UA1, UA2 looks somehow less like a large general purpose detector of the type that will come to dominate the field. It has high quality calorimetry arranged in a basically spherical geometry surrounding the interaction point. And it does have a tracking detector in the center labeled here vertex detector. But it lacks some other things that you might want it to have, like good or even really any hadronic calorimetry. And it also lacks, at least in this initial incarnation, any dedicated muon detectors. What it does have is this vertex detector, which is originally a multi-wire proportional chamber. But in 1983, just after the discovery in the W and Z, since the W and Z are there, there's certain to be a lot of physics that you can study at this collider. And it's going to be a number of years until the next generation of colliders come online. At this time, the LEP collider at CERN is already planned, but it's not going to take data until 1989. So people start thinking about what can we do to expand the physics reach of experiments like this. And one idea that people have is to install a more precise vertex detector. Well, the things that they can measure well with this experiment are basically electrons using their electromagnetic calorimetry and jets using mostly the vertex detector to reconstruct the trajectory of charged particles. But this multi-wire proportional chamber, sort of by its design, is not as sensitive in the direction along the beam as it is in the direction transverse to the beam. So if you want to be able to make measurements kind of like the ones we talked about that were being done at the Petra Collider in Germany, where you're trying to make the whole arrangement of the event in momentum space and group particles together in jets and look at the sort of angular distributions of those jets. Both the W and Z decay hadronically a lot of the time. And so this helps you to analyze the production of those particles in the hadronic mode, something that these experiments aspired to look at, but also just to study jet production in proton-antiproton collisions, which was not really seen by previous generations of proton colliders, something that up until now had been the purview of E+, E- machines. And so people had the idea to upgrade this experiment by adding a new detector to the vertexing part of the apparatus. And in fact, this was sort of a new type of detector overall. And it's this detector, which is shown here, which is their silicon vertex detector, something that will become basically standard in experiments after this. It was first implemented by UA2. So semiconductors often but not exclusively germanium semiconductors, have been used before this for a long time, especially in nuclear physics. So dating back 60 years or something, nuclear physicists have used semiconductor detectors as counters. They typically have two layers of longitudinal segmentation. So there's a thin layer at the beginning, which delivers a DEDX measurement and therefore is useful for identifying what type of particle is traversing the detector, and then a thicker, what we would call a total absorption calorimeter in the back, which measures the energy of these particles. But this is a destructive measurement since the particle is absorbed in the detector. And these types of detectors are optimized for nuclear physics and therefore for measuring particles in the MeV range. They would have an insufficient depth to contain showers in the GeV or tens of GeV range that particle physicists are most interested in. So in order to use silicon as a sort of non-destructive tracking detector to be able to image the particles coming out of an event without absorbing them, one basically needed to wait for the industry of manufacturing silicon to advance to the point where you could fabricate small, and by small here, I mean 50 to 100 micron feature sizes on a thin silicon wafer. Silicon strip detectors of the kind that I just described had already been in use for at least a couple of years before UA2. There was an experiment at the SPS North area called NA11, which used silicon microstrips in a fixed target geometry. But this detector, the UA2 silicon vertex detector, would be novel, both for its location in the center of a large collider experiment, but also for its innovative pad geometry, meaning they're not long strips by analogy with wires in a wire chamber, but individual squares of a checkerboard, if you will. Small square readout units, which can be read out independently. And this improves the sort of 2D accuracy on the sensor. So you're not just measuring one coordinate, but two. And then by arranging arrays of these detectors, for example, in concentric circles around the beam pipe, one can have a very good 3D accuracy on the hit position. So they put in a single silicon pad detector at first. It worked well. And this encouraged them to develop a second, more finely segmented inner silicon pad detector. And this is the version which is looking closer to what we would call a silicon vertex detector in a modern experiment. So you had to sort of fit this inner silicon pad detector in the space, in the gap between the existing silicon pad detector, which has a cylindrical geometry, and the beam pipe. So there's a very limited space to fit it into. There was basically a 9 millimeter radius gap between the beam pipe and the existing silicon pad detector for this new high granularity version to fit in. And 9 millimeters was just enough space for this thing with basically no dead space. So the size of the pads in this geometry is 17 by 33 millimeters with 3,072 channels. Both of these are sort of laughably coarse by modern standards, but it did represent a real pushing of the technological envelope at the same time, at this time. It was the first example of a silicon tracker whose geometry was adapted to a collider experiment, and therefore it's sort of the common ancestor of all the present silicon vertex detectors. There were many challenges to integrating this, and many of these challenges will be things that people working on more recent vertex detectors will be familiar with. I already mentioned the available radial space, less than 1 centimeter, including the sensors, but also the electronics and any associated circuit boards and services need to be brought in. This is a challenge which all detector builders face, but nobody more than people making these silicon vertex detectors, which want to be not only very close to the beamline for reasons we'll articulate in a moment, but also relatively many electronics channels, mean that there's an assortment of signals to be brought out, voltages and cooling, et cetera, to be brought in. So there's always a challenge of mechanical integration. The other enabling technology to be able to do this is that it would be impractical for so many individual electronics channels to actually bring out the signals individually on individual wires for all these thousands of pads. And so this is a detector which uses the idea of an integrated readout chip, which sits right on the detector, basically sandwiched on top of the silicon detectors themselves, in order to aggregate, do some processing of the signals from the detector and like serialize it onto individual links so that a more reasonable multiplicity of signals can be brought out of the detector. So this is also a place where the engineering of ASIC stands for Application Specific Integrated Circuit. This is basically a circuit whose function is not general, but at the time that you make the chip, you decide what it can and can't do, and then the functionality can't really be altered after that. These play a critical role in our experiments today. This is one of the first applications in a particle collider. We talked with the multi-wire proportional chamber about how the miniaturization of electronic components enabled you to fit all of these wires and their associated readout chain into a reasonable volume that experiments could accommodate. And this switch now from just miniaturized but discrete electronic components to integrated circuits where all of the individual components are basically burned onto a chip represents the next step in that evolution. I'm not going to go into the details about the ASICs used on this experiment, but I think we will talk later on, for example, when we talk about the LHC, about the importance of ASICs to particle physics. So let's keep that idea in mind. But for now, I want to talk more about the detector active elements themselves than the associated electronics. So why go to all this trouble to build a detector with this high level of segmentation and try to sandwich it in so close to the beamline? There's a very nice treatment of this problem in the textbook by Kolonowski and Vermes, which I have cited in the syllabus for the class. And the following sort of argument is adapted from their book. If you want to know more of the details, you can go there to find it. But a good example of why one might want to introduce a silicon vertex detector to a collider experiment can be seen by thinking about the physics of tau leptons. So tau leptons are a particle of the Standard Model, which is interesting to study. They've just been discovered not even a decade ago in the experiments by Pearl and his colleagues at SLAC. And tau leptons kind of fit into a zone of lifetimes where it's just possible to imagine building a detector which can reliably measure the distance that they travel before they decay, compared to heavier particles like the W and Z, where measuring the decay length in a direct way would be basically impossible. Another set of particles which has this property are B hadrons. Those of you who work on CMS will probably be familiar with the idea of B tagging, which basically works exactly the same way as this. But let's just follow the tau lepton thread for a moment. So tau leptons have a lifetime of about 290 femtoseconds, or 0.29 picoseconds, which is a really tiny amount of time to measure directly. So there may be some very high precision timing things done in experiments using, I don't know, laser pulses or something that are sensitive to these kind of femtosecond type things. But it's very difficult to imagine how you could directly measure that time with a stopwatch of a kind. But thankfully, relativistic physics helps us out a little bit here, because typically these particles are being produced not at rest, but with some kind of boost. And in the sorts of experiments we're going to talk about today, where we're looking in detail at the properties of the Z boson, for example, the typical momentum with which these particles are produced, if I produce a Z at rest and it decays into 2 tau leptons back to back, then each of those tau leptons is going to have a gamma times beta factor of more than 25, which means that the decay length that I measure in the lab frame, which is given by this product gamma beta times the speed of light times the typical lifetime of the tau, comes out to be about 2.2 millimeters. So as measuring a time of 290 femtoseconds by itself is extremely challenging, measuring a distance of 2.2 millimeters with a tracking detector is possible to imagine. And so people are going to go out and figure out what are the parameters of the detector I need to build to surround my interaction point if I wish to be sensitive to decay lengths on this order. And again, if I'm interested in measuring the decays of B hadrons, there's another thing that we'll talk about later on. The argument is basically the same, just with slightly different numbers. So it's possible to figure out what the geometry and properties of my detector need to be in order to resolve this distance by doing a simple exercise thinking about the position resolutions of detectors at different distances from the beamline and how I can combine information from multiple layers in order to minimize the resolution on the overall distance that I'm trying to measure. So imagine for a moment a very simple vertex detector, which consists of just two planar layers. They sit at two radii, R1 and R2 from the interaction point as pictured here. We'll call them detector 1 and detector 2, corresponding to R1 and R2. Each of these layers has a position resolution, sigma 1 and sigma 2, which you could imagine is related closely to the feature sizes on the silicon detector element. So if I had, strips of width 50 microns on my silicon wafer, and that was my detector, probably these position resolutions are going to be similar to that number 50 microns. We'll talk a little bit later on about how we can improve on that slightly by exploiting the charge sharing between adjacent strips, but let's just imagine that this resolution is basically the detector size. In this analysis, we're also going to neglect any curvature of the tracks and assume that the sensors have a simple planar geometry. You can handle both of these things perfectly fine, but it doesn't really change the overall conclusion, so we just leave it out of this example. Let's first consider the case where detector 2 is perfect, which is like setting sigma 2 to 0. That's shown in subfigure A of this picture. Then we can use basically these geometric argument, the similarity of triangles. If we're working from a hit on detector 2 back to the beamline, and we use detector 1 to try to constrain the direction that that particle was traveling, or put another way, the location that it was traveling from, what would we find out? We would find out that the error on B, which is the distance here at the bottom, that's like the uncertainty projected back to the beam spot location, is going to be related to the ratio of these distances, R1 and R2. So for sigma B over sigma 1, setting sigma 2 to 0, then that uncertainty is just going to be R2 over R2 minus R1, basically taking this triangle here, and since it's similar to this other triangle, we can solve for sigma B here. Straightforward enough. And we can repeat the exercise using the opposite assumption. So now we say that sigma 2 is non-zero, but sigma 1 is 0. Again, we draw a diagram which is similar to the first one. So now we have, again, similar triangles of different side lengths. And here we can see that sigma B, again, the measurement we're trying to make at the beam spot, divided by sigma 2 is equal to R1 over R2 minus R1, again, exploiting the similarity of these triangles. Now we can add these two terms, one which is depending only on sigma 1 and one is depending on sigma 2. If we assume that the measurements are uncorrelated, these are two independent detectors that don't share any electronics, whatever, then we can just add them in quadrature. So we would get sigma B squared is the sum of these two terms, rearranged to put sigma B by itself in quadrature, plus a third term, which we'll call sigma MS, that's related to any like multiple scattering of the particles on their way through the material, which we didn't account for in the first two examples, but let's just assume that it's a flat thing. This is not really true. Different particle species have a different dEdx as they pass through the same amount of material, blah, 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 blah. But this is just a simple model to try to get us inspired to thinking about how we should design our silicon vertex detector. So already with this, this simple expression, I think there's a couple conclusions that you can draw about how your vertex detector should look. First, the resolution of detector 1 is always going to be more important than detector 2 due to the coefficients being proportional to the radii. By definition, R2 is larger than R1, otherwise they would be reversed. And that means that this coefficient here shares the same denominator with this coefficient here impact of the resolution of detector 1 is always going to be larger because R2 is larger than R1, and these ratios are otherwise the same. So that means if I'm going to pour money and engineering effort into shrinking my detector channels, I had better put that effort into the layer which is closest to the beamline, which I think makes intuitive sense, but it's nice to have a model that shows exactly quantitatively how that dependence might go. The second point, which is maybe also intuitive, depending on how you think about this geometry, is that this lever arm, the distance between R1 and R2, appears in the denominator of both of these terms in the expression, and therefore increasing this lever arm, either by moving R1 closer to the beam pipe or moving R2 further from the beam pipe for the same resolution, will tend to increase the resolution. So it's probably not a good idea to design a detector which has a super precise layer very close to the beam pipe and then another one just behind it, because the information that's measured by the two of those will be largely overlapping. If we're limited to 2 layers, we should probably put our second layer further away, all else being equal. Although that will also have some downsides, right? The further away I put layer 2, the larger the surface area of layer 2. So if I'm paying like per unit area for silicon, then moving R2 to be larger will increase that cost. But still, this lever arm R2 minus R1 serves to increase the resolution. And sort of a corollary of that is that R1 should be as small as possible. That both increases the lever arm and helps us with this issue of material cost. Finally, the resolution degradation due to multiple scattering, this third term, which we didn't really go into the details of, but I think we can just see that we would like to keep this as small as possible. And if all else being equal, smaller than the other terms, that means that I should try to make my detector very thin. So not only the active material itself, but also any circuit boards or anything else that I need to glue it to in order to make my detector module. I should keep it as thin as possible so that this third term doesn't dominate. So there's an era of time here during like the 80s and 90s when both multi-wire proportional chambers and semiconductor detectors are used, sometimes in combination, in different experiments. And each of these detector technologies comes with its own trade-offs. I mean, we still use gaseous detectors in some experiments because they do still have some advantages relative to silicon, although the importance of silicon or other semiconductors has grown a lot relative to these sort of infancy in the early 80s. So first of all, the density of semiconductors is much higher than gas, which is helpful, but also harmful. It's helpful in the sense that we have a higher DEDX crossing the material. So if I want to produce the same amount of charge, for example, in order to interface to a readout electronics that needs like a certain amplitude of signal to be able to see the particle going through, I'll get a higher DEDX from the semiconductor detector than from the gas detectors. But this also comes along with the downsides of higher DEDX, more multiple scattering in the material, and also more possibility for nuclear interactions. Semiconductors, as we'll see in a few slides, the physics of the charge generation is also a bit different. Instead of knocking an electron off of a gas molecule and then leaving behind a heavy positive ion, here we generate an E-hole pair in the semiconductor whose effective mass is much smaller. So there's more charge generated per unit energy loss, and this aids us, for example, in better resolution, whether that be resolution on the amplitude of the DEDX or indirectly the position resolution through like charge sharing between adjacent detector channels. All else being equal, having more charge per unit energy loss will improve the resolution of my detector without affecting the particles any differently. For semiconductors, there's no pressure vessel or container needed to stop the gas from escaping. This may be an obvious point, but if you have something like a multi-wire proportional chamber that relies on a specific gas, we obviously need to keep that contained in some kind of vessel. If the gas is pressurized, That vessel has to be strong enough to contain the pressure. And any kind of pressure vessel is going to introduce basically dead material to the detector. It may still be worth it, but one nice thing about semiconductors is that they can just kind of be positioned in free space. Semiconductors can have a microstructure imprinted on them by industrial processes. So the way that silicon detectors are made is by a process of, there are many different industrial processes which are applied to silicon in order to turn it into chips or turn it into particle physics detectors. There's a photolithography part where you use extremely short wavelength radiation with a mask in order to sort of prepare the surface of the material for different treatments, which can then leave chemical impurities in a controlled way on the surface or built up even on top of the surface in some cases. And there's a variety of techniques that are used to achieve these kind of three-dimensional stack-ups and structures in silicon. So there's etching, implantation, material deposition. Depending on the producer and exactly what kind of thing they're trying to produce, they may use one or all of these techniques in order to build up a structure on the silicon. And that structure, I mean, for cutting edge chips now, the structure may be as small as single digits nanometers. Typically, that's not useful for us in high energy physics, and the cost of building a nanometer pixelized thing would be something we probably could not pay. But certainly structures on the order of a few hundred microns or even a few tens of microns are achievable and useful to us. And it's difficult to produce such fine pitches in gaseous detectors using wires. Finally, as a pure drawback, semiconductors are very expensive relative to gases. And so instrumenting a large volume is similarly costly. The cost that you should have in mind for something like the silicon tracker of an LHC experiment is order of $100 million or Swiss francs or whatever currency you want to choose. And so that obviously limits a lot how many of them you can build and who is able to build them. And yet it is still judged to be worth it because the positive properties of silicon are able to deliver a physics performance that's hard to imagine delivering in any other way. These semiconductor detectors for charged particles or radiation are, of course, not confined to particle physics at this point. They're deployed for a variety of different uses, apart from science. For example, X-ray detectors increasingly use these solid state detectors, and that can be in the medical field or in biological research. Even material science, X-rays are an important enabling technology. Radiotherapy, so people who are having their cancers, for example, treated by particle beams or by radioactive sources. Semiconductor detectors can be used to align and control the direction of those beams as well as their energy and their purity in terms of the desired particle species. So there's sort of a feedback loop that develops during these decades. We as particle physicists motivate developments that make their way into industry, but then we also benefit from the industry around these type of detectors growing larger, and we benefit from producers who have really optimized for making large volumes of these kinds of sensors, and we can benefit to some extent from the economies of scale that are created. So just a brief word on what a semiconductor actually is for those of you that may not be very familiar already with this terminology. So there's a basic quantity called resistivity. This basically tells you how many ohms of resistance I will pick up in passing through like a wire of a given length. And this is one of those physical quantities that varies an enormous amount from element to element and from chemical compound to chemical compound. On the far left of this plot, we have things which are considered to be insulators. Those would be things like rubber or glass or diamond or quartz. These typically have electric resistivities on the order of 10 to the 18 or down to about 10 to the 10 ohm centimeters. So for a specific geometry, you would expect these things to have resistances with many billions of ohms per centimeter of material. And this resistance is so high that basically electricity does not flow through these materials. In order to apply high enough voltage to overcome this resistance, you would cause all kinds of heating and so forth, and basically destroy the material before you could get it to conduct any appreciable amount of electricity. On the other side of the plot, we have conductors, which are typically metals. Metals are metals because they contain unpaired valence electrons, and they can basically form a solid which has electrons which are free to move around in the solid. And so they're conductors because if I like push on an electron at one side of the conductor with an electric field, being free to move, it can then transmit that push to the next electron in line and so on and so forth through the material. So if I apply a voltage, I will see a current flow, and that's electrons basically drifting through the conductor under the influence of an applied field. Semiconductors are somewhere in between. They have resistivities in these units which are of order 1, maybe up to about 10 to the 4th and down to about 10 to the minus 4th. And these ranges can be controlled by how exactly we build the device, how many impurities we introduce / allow to remain in the material, and the electronic properties of the different semiconductors we use. Silicon is the one that's going to be by far most important for our particle physics usages. Germanium, I already mentioned, is used a lot in nuclear sort of total absorption counters. And there are other semiconductors which are under consideration for future particle detectors and or have applications in electronic engineering. Things like gallium arsenide or cadmium sulfide can have desirable properties depending on exactly what job you're going to do. But almost everything we're going to learn about semiconductors here, I think we can learn from analyzing the example of silicon with appropriate doping. Your sort of microscopic quantum mechanical picture here should be that there are bands in these materials. There is the valence band, which basically corresponds to the energy of electrons that is just sort of freely available in the material. And then there's a conduction band, which is how much energy electrons would need to have in order to be sort of freed from their local atom and traveling through the material without being tightly bound to the original atom. So in the case of a metal, these bands overlap, right? The valence electrons are sort of already naturally in the conduction band. And if you put a bunch of copper atoms next to each other, the electrons will freely move along that wire without feeling any particular attachment to the original atom. In an insulator, those outermost electrons are so tightly bound that we would need to apply huge energies in order to free them, and that would otherwise disrupt or destroy the material. And so it's basically impractical to imagine getting enough energy to these valence electrons to like move them into the conduction band so that they can move around. And semiconductors are the sort of compromise between the two. The conduction band is separated by the valence band such that if I don't do anything, electricity is not easily going to flow. However, by either introducing some additional energy to the material and or by changing a little bit the electronic structure to monkey around with the exact distance between these bands, I can put myself in a situation where current will flow under some conditions and not under others. And that's the situation that I want to be in order to make a semiconductor junction, which will work as a particle detector. You see labeled here this Fermi level. That's sort of the median energy level available to the electrons in the material. So consider this to be like the energy level at which the states are sort of 50% populated. And it's a good sort of benchmark for, you know, how far away my conduction and valence bands are from this Fermi level. Helps me to understand what the properties of the material with respect to electricity will be. As I said before, silicon is by far the most widely used material for semiconductor detectors in particle physics. Not only are the active materials normally made of silicon, but the readout chips that are required in order to use them are also made from silicon. Silicon is an extremely common element on Earth. After oxygen, it's the second most common element in Earth's crust. It makes up about 28% of the rock that Earth is made of. But it only occurs in compounds in nature, the most common one being silicon dioxide, basically sand or glass. Because pure silicon is extremely reactive and will instantaneously oxidize into silicon dioxide given the chance. So actual silicon as a bulk material has to be produced under very tightly controlled conditions in the lab where we keep oxidizing materials far away, so it can build up these sort of crystal boules that you see in the picture here. So you basically start with something like sand, and then you perform a chemical reduction using a base metal like aluminum or magnesium, or at the industrial scale, sometimes with carbon in an arc furnace. This is called a carbothermal reduction. And this is a way that you can start to build up quantities of elemental silicon. However, 95% purity is nowhere near the level of purity which is required for microelectronics or particle detectors or photovoltaics. There's a number of different processes that can be used here. There's something called the float zone process, where you basically have a high temperature region along your ingot of impure silicon, and that high temperature region basically allows silicon crystal matrix to form and pushes impurities out of it. There's something called the Kolkrasky process, which is a seed crystal which is mounted on a rod, is dipped into a molten bath of silicon, and you allow the crystal to grow from the seed crystal, and then you sort of slowly pull this thing up as you continue rotating it, and this creates the ideal environment for silicon crystals to grow off of the seed, and that's how you end up with these sort of spun-looking ingots. I think basically all the silicon that's used in the applications we're talking about now is grown using this second process, and that's because these CZ rods can be grown to large diameters. For example, in the HGCal project we're doing in CMS now, we have 8-inch sensors, so that's like 20 centimeters or so. It would be impossible to grow that thing by the float zone process, and only this seed crystal in a molten bath can produce ingots of that diameter. These things are then diced into wafers. You see here these highly polished, reflective wafers. You obviously want the surface quality to be very good in order to be able to do, lithography or ion implantation or whatever. You don't want any mechanical waves or rough surface or anything that can interfere with this sort of like atomic level engineering that you're going to do to get the exact number of impurities to the exact location that you need in order to alter the properties of the silicon. There's also something to be paid attention to here in terms of the crystal matrix of the silicon and the direction that you cut it. So silicon crystal grows in this so-called diamond lattice. So for each of these cubic volumes, imagine a atom at the center and then atoms at 3 opposite corners of the cube, and then that pattern is repeated over and over again. So actually, when you're dicing this thing into wafers, it can matter depending on the application if your dicing direction, how it's aligned with the crystal structure. So like dicing in the vertical versus horizontal versus diagonal planes here will result in different orientations of the crystal with respect to your wafer, and that effect can be important depending on what you're trying to do. Maybe you've seen these so-called, I think they're Miller indices. It's like 111, 110 notation, which tells you about the orientation of the crystal lattice with respect to the plane of your sample. Once you create these wafers of pure silicon, you can introduce impurities in a controlled way that will disrupt this crystal lattice structure in a way that you either have excess unpaired electrons. You see the conduction electron here, which is produced by putting a arsenic atom into the place of a silicon atom in the crystal matrix. So arsenic compared to silicon has one additional valence electron. If you sort of force him into this structure of crystal, he's going to end up with that extra valence electron unpaired with anything, and therefore more free to move than the paired electrons in the covalent bonds between the different sites in the lattice. And so doping with arsenic, as an example, is a way that we can create excess conduction electrons and modify the band structure of the material in the way that we like. Counter example is boron, which has one fewer valence electron than silicon. So if we replace in the lattice a silicon atom with a boron atom, then there will be a lack of an electron, or if you will, an excess hole. And it turns out that this hole is also free to move under certain conditions through the lattice. So you can imagine that process as like, if the hole moves here, it's because the electron moved here, et cetera, et cetera. You can see how that affects the band structure of the material in the example of N doping, which is the arsenic example here, where you have an extra electron. You basically create in the electronic structure of the material a new energy level closer to the conduction band, which has electrons which are easily available. So this will make it, all else being equal, easier to move electrons into the conduction band because we've created a new population of electrons at a higher energy closer to the conduction band. And then for p doping, this is analogous, just in the other direction. We haven't built a particle detector yet. We've just built a piece of silicon that has either excess electrons or excess holes, depending on how we've doped it. If I want to make this thing into a particle detector, what I need to do is take a p-doped material and an n-doped material. There are other junctions that you can make, but the p-n junction is the most classic one and the easiest example to explain. By bringing two parts of material that have different doping levels in contact with one another, we form what's called a junction. And this junction is itself a particle detector for the reason that I'm about to explain now. So when I have this p-doped material and the n-doped material, and I bring them into contact with one another, you know, in the p-doped material, there's an excess of holes. In the n-doped material, there's an excess of electrons. And that means at the junction between the two, there's going to be some diffusion of electrons from the n-doped material towards the p-doped material, and some diffusion of holes from the p-doped material, drift of holes from the p-doped material towards the n-doped material. And in the region of the junction, those two effects are going to cancel out. So electrons and holes will combine to basically deplete this region in the center of free charge carriers. And in fact, we call this the depletion region. And then we can apply an external voltage to sort of manipulate this depletion region. If I apply a forward bias, that is, I attach the positive side of a battery to the P side of the junction and the negative side of a battery to the N side of the junction, that's called forward biasing. So we're basically supplementing the natural tendency of the material on this side to donate positive charges and the material on this side to donate negative charges by supplying them more of what they're already donating. And this will have a tendency to increase the size of the P and N regions at the expense of the depletion region in the center. So basically, if I provide a sufficient voltage to overcome the gap in the band structure between these two sides, then I will get current flowing in the forward direction. This is a classic diode behavior, right? At zero or very low voltages, no current flows. As I supply enough external voltage in order to overcome this depletion region in the middle, current starts to flow in the forward direction. And then once we exceed the critical current, then the more voltage I apply, the more current flows. What's more interesting, usually for us in the particle physics case, is the opposite situation where I apply a reverse bias. This means I put the positive side of my battery against the negative dope, the N-doped side, and the negative side of my battery against the P-doped side. This serves to actually inhibit the drift and diffusion of free carriers into the depletion region in the middle, with the effect that the depletion region grows. And I would need to have a very large reverse bias in order to overcome this large depletion region and get current flowing in the opposite direction. So the material, unlike in the forward bias case, very strongly resists current flowing in the other direction because this depletion region is growing the bigger the voltage that I apply. Eventually, there's a breakdown. If I apply a larger and larger reverse bias, eventually I can get myself into a condition where current is flowing in the reverse direction. This is sometimes used to characterize sensors for particle physics, but it's generally not a useful operating condition for being a particle detector. For that, I want to be in this kind of reverse bias regime. And the degree of that reverse bias is going to depend on many things, including the exact properties of the semiconductor that I fabricated, the geometry of the situation, how large I want the depletion region to be relative to the thickness of the detector and the amount of charge that I want to be produced when charged particles go through, et cetera, et cetera. But basically, in this reverse bias thing, I've created a situation which is more or less analogous to like a gaseous detector of the kinds that we discussed way back in the first lecture of like a Geiger tube, right? This is basically the same situation. I have positively and negatively charged electrodes, and then I have material in the middle. In the case of a Geiger counter, it's a gas. In this case, it's the depleted silicon in the middle. And there's no free charge carriers in there, so there's no current flowing until a particle goes through. When a particle goes through, it produces free charge carriers in this depletion region in the center, and then those charge carriers will flow to the oppositely charged electrodes. And as that flow occurs, I'll see a spike of current, and that gives me the idea that a particle went through. Just as an aside, the size of this depletion region being related to the reverse bias that I apply, you can think of this situation as being like a parallel plate capacitor. As we know, the capacitance of a capacitor depends on the dielectric constant in between. So for like silicon, you could go and look that up, but also on the separation between the plates. So basically, as I change the bias, the reverse bias voltage on this junction, the depletion region is going to grow and shrink according to that voltage. The higher the voltage I apply, the larger the depletion region. And as a result, the capacitance is going to shrink as I apply a higher and higher voltage, right? So up to some limit where this region grows to encompass the whole distance between the P and N junctions, there's basically no more material left to deplete. I can sort of analyze and characterize the geometry of the sensor by monitoring how this capacitance changes in response to the voltage that I'm applying. So you'll often see these types of measurements, the curve of the capacitance versus the voltage. You see that the capacitance is steadily decreasing as I increase the voltage. That's like separating the plates of my parallel plate capacitor. And then eventually I reach this point where it's fully depleted and I stop seeing a change of capacitance. The capacitance of the sensor also affects its frequency characteristics. So just like a RC circuit in electronics, you know, the capacitance is going to affect basically what frequencies my detector can and can't respond to. And so the capacitance of my detector, which is going to be related to the materials that I chose and the depletion voltage that I apply, is going to have some implications, for example, how fast the signals are intrinsically coming out of this detector. And, you know, I can always slow down and shape the signal more by introducing additional impedance in the readout chain, but it's very hard to ever get the signal faster than what originally came out of the semiconductor. And so this will place some upper limit if I have a desired time response, like how physically large my individual channels can be or vice versa. I see Jose has a hand up.
Hey, yeah, maybe can you hear me?
Yes, I hear you. Go ahead.
Maybe you say it, but I'm a little bit confused. So in this PN junction, there are two materials, but the material in between the depletion region is which material, P or N, or is a third material?
So what you should imagine here is that the p-doped and n-doped materials like go up to the interface between the two. So before I connect them, it's like all p on this side and all n on this side. And then as soon as I touch them together, even though one side is p-doped and one side is n-doped, this like diffusion of electrons and holes into the center will create a depletion region, even though if it wasn't touching together in a junction, that area would still have an excess of p-type carriers. Does that make sense? So there is no third material. It's not like I put like bulk silicon in the middle. I have p-doped. In the simplest case, I just have p-doped material on one side and doped material on the other side. And when I bring them into contact, a depletion region forms because the excess electrons on one side and the excess electrons on the other cancel each other out. So those like arsenic and boron atoms are still in that middle region. It's just that the charge carriers that are normally associated with them have been depleted because they've combined with a nearby hole or nearby electron, as the case may be.
So somehow this region is made out of the two material. I mean, there is one part of the depleted region in P and another part in N.
Exactly. So the location of the dopant doesn't change when I make the junction. It's just that because there's some limited mobility of the charge carriers, that when I bring them into contact, it forms a region which is depleted in charge carriers, even though the parent dopant atoms are still there.
All right. Thank you.
So as we said, now that we formed this depletion zone, it basically serves the role of our active medium for particle detection. The particle goes through, it loses energy by scattering off of the electrons in the material. And each time that an electron receives a little kick of energy from the particle going through, it can be moved into the conduction band, and the same thing for the holes. So no, under the reverse bias condition, no or little charge can flow. But when I produce these electron hole pairs by scattering off of the material, my charged particle of high energy gives up some of its energy to the electrons, and those electrons then trickle back to the oppositely charged electrode and vice versa for the holes. And so what I'll see is that there's some characteristic time for these electrons and holes to sort of filter through the material and get back to the electrode. And that's the time that is going to determine the sort of rise and fall of my detector response. So for typical choices of thickness of the depletion region and bias voltages, which are again going to be a little bit different depending on your application, but these are sort of representative values that like the electrons tend to arrive first. For reasons that are too complicated to really go into here, their propagation speed through the material tends to be a bit faster than the holes. The electrons are typically arriving in a few, like under 5 nanoseconds, and the holes are then arriving completely only a little bit later, let's say 8 to 10 nanoseconds later. But this sort of sets the characteristic time for collecting a signal from a detector like this. So the intrinsic time resolution of these detectors is going to be on the order of a few nanoseconds. With careful design of the electronics, one can really shape the current pulse by, for example, stretching it out in a way which doesn't change its overall characteristics too much. And then you can try to have a discriminator circuit, which makes a very careful measurement of exactly when it crosses some threshold. And so you'll see that in, for example, the current HL-LHC upgrades, you have the aspiration to produce timing measurements on the order of like tens of picoseconds, which is sort of below, on this plot, it's only a fraction of the way between 0 and 1 nanoseconds. But you have to do quite a bit of work to build the appropriate sensors and the appropriate electronics to reach that level of precision with the sort of normal silicon detector, you're going to be talking about time constants on the order of nanoseconds. There's also this phenomenon of charge sharing between different electrons. This applies to pixelized or pad geometries as well as strip geometries, but in both cases, the idea is the same. So in this depletion region, if I'm sort of between two strips of the readout, there's some probability that my electrons are going to flow. In this case, it's showing the flow of the holes. So there's some probability that my holes are going to flow to strip 1, but there's also some lesser probability that it's going to flow to strip 2. And that has to do with the details of the sort of random walk that these things take through the material as they're being accelerated by the electric fields. So you might naively think that we would want to reduce this charge sharing between adjacent strips as much as possible. And there are detector types where you would like to do that for different reasons. For example, in photodetectors, your actual dynamic range of your photodetector will be greater if there's less crosstalk between the channels. And so you might artificially increase the separation, for example, between these detector elements to reduce as much as possible the chance that some of the charge goes to strip 1 and some of the charge goes to strip 2. But in some detector types and geometries, actually this charge sharing can be advantageous. In particular, if this sharing is modeled well, then you can achieve a position resolution on the location that the particle went through your detector, which is better than the pitch of the strips, which is better than the distance between the strips. So in some cases, you sort of intentionally cultivate this charge sharing in order to be able to make some inference about where along this line between strip 1 and strip 2 the actual particle arrived. There are also complications having to do with the fact that often these detectors are inside of magnetic fields. For example, in a lot of these collider experiments, the central tracker is intentionally in a quite strong magnetic field so we can measure the bending of the particles. That will also, as you can imagine, affect the direction that these electrons and holes propagate through the material. Since they're charged particles themselves moving through this strong magnetic field, they're going to feel the Lorentz force on them, and that's going to result, depending on the geometry and the situation, of the charge carriers tending to travel along diagonal lines in this volume rather than straight towards the electrode. And so if you're trying to weight the location of the hit according to charge sharing between strips, you would better calculate and be able to model the effect of the external magnetic field on the propagation direction. So having gone through that sort of lightning tour of silicon detector physics, we can now go back to look at this one more time and see how it's really not that different from modern detectors in concept. You have the actual strip lines on the silicon here. Each of these lines is then connected to channels of your readout chip. The readout chip then collects the charge from each of these individual channels, digitizes it, and puts it onto some sort of high density interface to move off detector, where then you'll have hits per strip, and sometimes their amplitude, sometimes their time, depending on the readout chip associated with each of these hits, and that all feeds into an off detector reconstruction that can look at things like how much charge was shared between adjacent strips in order to more fully exploit the information which is available. And that's really it. I mean, the CMS tracker, while it's much huger and much more expensive and has way more layers and lots of clever innovative features like a different geometry to more fully surround the interaction point, these end cap discs, which have a orientation in the plane perpendicular to the beam line in order to more efficiently measure the trajectory of particles traveling through here, is basically the same idea as this UA2 detector, just sort of scaled up to the sort of ludicrous scale. Of course, there's always a drawback to having so much material here. As we talked about, one aspect in the resolution of the detector is going to be multiple scattering. And in this design in particular, the CMS tracker, there's a lot of stuff here. There's a lot of carbon fiber to hold all these guys in a precise way in their orientation in space around the interaction point. There's a lot of infrastructure devoted to cooling. There's a lot of electronics infrastructure, the chips, but then also all of the control electronics and the cooling that's necessary for the care and feeding of the chips, power converters, all these things that are sort of distributed throughout this volume. And so as a result, you can, if you're not too careful, introduce a lot of material with this type of detector design. So one axis that we're always pushing is to figure out how to operate these things in the lowest power mode available, to simplify and streamline the electronics as much as possible in order to reduce the amount of infrastructure that you need to put in this space. That not only has positive, minimizing the material not only improves your measurement of the track parameters themselves, but also reduces the chance for things like electrons and photons to shower in your material, something that's actually quite likely in the current CMS detector. Depending on your line between here and the ecal, which sits outside the tracker, you may have more than one radiation length of material. And therefore, in some parts of the CMS detector, most photons will shower or at least convert before reaching the ecal, which has negative consequences downstream for energy resolution, et cetera. We'll talk more about the interplay between the different elements when we talk about large detector systems a few lectures from now. In any case, the discovery of the Z at the CERN SPS kicks off a sort of international competition in order to be able to make precision measurements of the Z particle. Since the Z can be produced in E plus E minus annihilation, this would be a very clean initial state. So unlike those pictures we saw from UA1 in the previous lecture, where there's kind of hundreds of tracks sprayed all over the place, Z production in E plus E minus annihilation gives very clean events and gives you the possibility to measure the properties of the Z particle very precisely. And there are some particular properties that are going to give us a wealth of information about the standard model. And so there's just sort of a race is on to be able to observe and carefully measure the properties of the Z in E plus E minus annihilation. The first and mightiest entrance into this race is CERN with its LEP collider. LEP stands for Large Electron Positron Collider. This shares the tunnel that the LHC will eventually use. So you can probably recognize on this picture that LEP is now what will be labeled LHC on the aerial view. This was initially planned even in 1976, just before the W and Z particles were definitively discovered, but there were good predictions on the market for what their mass should be. And so they already started the massive engineering effort to bore this huge tunnel of 27 kilometers around the CERN site. Remember that one of the limiting factors on electron storage rings is the tendency of electrons to radiate energy as they go around this ring. That basically drives you, if you want to make a very high energy electron-positron collider with a center of mass energy at the Z mass, which is about 91 GeV, eventually this thing would operate up to even higher center of mass energies, like above 200 GeV. Massive energy losses from synchrotron radiation. And so making this ring really large is one way to lower the amount of acceleration happening per unit distance traveled. And that's one reason why LEP is so big. This also sort of matches with the plan eventually to use this as a hadron collider. Even at the time people were digging this tunnel, it was already understood that the precession would be from LEP in that tunnel to eventually be replaced by the LHC. And there you had to consider, what energy you wanted to reach in the LHC if you wanted to, for example, cover the whole range of possible Higgs masses. Given the magnet technology that's available, this tunnel also has to be able to accommodate that. So this is an example of like very long-range planning by CERN in a way that's turned out to be totally successful. That like the huge investment to dig this tunnel for LEP has basically enabled a 50-year physics program at CERN, which is still sort of well underway. So I think it's a very impressive effort sustained over many decades to do all this physics. And it's something which CERN as an organization seems sort of uniquely capable of doing. There were 4 detectors built at LEP. This is a lot of general purpose detectors to put at one collider. And I think it's telling that in colliders since LEP, we have not attempted again to have quite so many general purpose experiments. One could question, for example, what the marginal benefit of like the 4th best LEP detector really was. But there was also huge interest and enthusiasm in this project. And so there was a desire to accommodate as many groups and nations as possible in the effort. There was not only huge European participation in these different detectors, but also participation from outside of Europe as well, the United States, India, Japan, et cetera. There's a tradition of international collaboration, which has sort of flowered even more in the LHC era. So while the specific number of detectors maybe seems a bit strange to us, the spirit of maximizing opportunities for collaboration has, I would say, served CERN well in the years since. This is maybe the canonical LEP detector called Aleph, using the Hebrew letter Aleph here. And it has a design which by now should look familiar. I would say that when you look at designs for even future E plus E minus collider experiments, they really just look like Aleph. One of the most interesting parts of this is the time projection chamber, which we haven't had a chance to talk yet about this detector technology, but we will. So I'm not going to comment too much on that. But just to say that we have the traditional combination of a vertex detector surrounding immediately the interaction point, then a sort of inner tracking chamber using wires in this case, then this time projection chamber, whose operation we'll discuss later, followed by an electromagnetic calorimeter, a superconducting magnet, and then hadron calorimeter outside of the magnet, and then finally surrounded by a layer of muon systems. And this thing is on risers so that it can be opened and closed. It looks really very much like the sort of generic particle physics experiment. And there were 3 other detectors, but you know, they each had their own different design philosophies and idiosyncrasies, but in general, they all aimed at the same physics, and the differences between different detectors are going to sort of grow less and less as we go to these bigger and bigger accelerators. It just becomes hard to justify dedicating an interaction point to a really single purpose experiment when the expense and the timescales are so huge. You had better maximize sort of the number of general purpose experiments that you can enable. But there were other entrants in this race as well. So LEP is slated to come online in 1989, but SLAC in California realizes that they can try to actually beat CERN to the Z particle by taking the existing linear accelerator and cranking up the energy again to the Z pole, and sort of in a more quick and dirty fashion building a collider at the end of their linear accelerator. At the end of this thing, they situate the Mark II particle detector, which obviously, including in its name, is a sort of direct descendant of the philosophy of the Mark I detector. Again, looking very similar in its design and construction to the other detectors that we've been talking about recently. They actually did succeed in getting collisions at the Z-pole sort of a few months before LEP was able to collect a really significant sample of Z bosons, but this collider always struggled with its luminosity. It improved over time, but it was never close to what was able to be achieved in the LEP storage ring, in part because having this linear collider geometry basically means that you can only use each bunch once. Whatever electrons don't sort of collide here in the center of the detector are lost forever, and then you have to accelerate the next bunch. And it also gets its one shot at colliding. So while they did observe the Z in E plus E minus colliders before LEP did, the luminosity was sort of disappointing. In July of the year 1989, they were able to report a Z mass of 91.11 plus or minus 0.23 GeV based on only 106 events. There is yet another collider coming online in this year, 1989. I think it's mind-boggling to those of us who are working on sort of the LHC now, the idea that 3 sort of energy frontier machines would open not only in the same era, but in the same few months. As we mentioned when we talked about the Fermilab Accelerator Complex a couple of lectures ago, the plan, even from the early days of these sort of Berkeley Bevatron studies, was to eventually take this main ring and use it in order to feed a storage ring for a proton antiproton collider. And that project sort of consumed the 1980s at Fermilab into the 2000s. And it also started taking data in 1989 using what was called the collider detector at Fermilab, or the CDF experiment. This is built again very much in the UA1 mold with hermetic calorimetry, including end caps, which can be brought in to sort of seal the experiment. A central detector, which is initially using wire chambers in order to do the measurement. Eventually, this detector will be outfitted with a silicon vertex detector for future runs, and a second experiment, D0, will come online starting in the 90s, which will eventually be upgraded and augmented to have a physics capability similar to CDFs. In any case, they're sort of pursuing the Hadron Collider path that UA1 and UA2 had already trod in discovering the Z. They collect by later in 1989 a total of 4 inverse picobarns. They get 188 Z events that they can find. They are able to do a bit better than SLAC in terms of the mass resolution. But really what people are waiting for is to see the full results from LEP, where those experiments are expected to have thousands of events each, and there are 4 of them. So they're going to very quickly blow past SLC and the Tevatron in terms of the precision of their measurement of the Z mass. People are particularly interested in the Z mass and its width, not just the central value of its mass, but also the width of the resonance. And the reason for the interest in the width of the resonance has to do with the Heisenberg uncertainty principle. So the Z lives only a very short time, and so it's not really possible to measure its lifetime directly, but one can measure its width. For example, if you have a collider whose energy you can scan, you can measure the cross-section for Z production as a function of the energy and basically map out the width of the resonance. The width of the resonance is inversely related to the decay time because of the uncertainty principle, right? So H bar is the sort of constant of proportionality between our uncertainty and the energy of the system, that is the mass of the Z in this case, and the decay time, which in the case of the Z is so tiny as to be unmeasurable, but the width is possible to measure. It's several GeV wide. And so if you have good control over the energy of the accelerator, you can map out this line shape. That's particularly interesting for experimenters because this line shape, the width of this thing, is proportional to the sum of the widths into individual decay modes. So we can indirectly infer how many invisible decay modes the Z has if we measure the visible parts of the width, that is the cross-section times the branching ratio into hadrons, the branching ratio into the visible leptons, like electrons, muons, and taus, which we can measure pretty well. And then a third piece, which is invisible, that has to do with neutrinos. So at this point, people are curious if there's, for example, a 4th generation of matter particles beyond the tau and the bottom. One indirect way to test that hypothesis is to measure this overall width by scanning the shape of by scanning the energy of the machine and mapping out this distribution, and then comparing to the cross sections and branching fractions for these visible decays. That will let you indirectly measure this invisible part. Since you can calculate this lambda for a light neutrino from theory, basically the difference between the width that you observe and the partial widths that you count for the hadrons and the leptons can tell you how many species of neutrino there are. So if this N nu turns out to be 4 instead of 3, that would be a strong indirect evidence that there is yet a 4th generation of matter particles to be measured. This technique depends on understanding the energy of the collider well. In order to map out this line shape, what you're going to do is take runs, say, every few hundred MeV, starting from like 89 GeV going up to 93 GeV or something, and basically building up the picture of this width, all the while measuring how many events you see in the visible channels, leptonic and hadronic decays of the Z. It's actually harder than you might think to absolutely measure the energy of the machine. Of course, you have your model of how energetic the electrons are, and that sets, the current and the bending magnets and stuff. But then that all has to be tuned as you bring the accelerator online, and you lose sort of the absolute calibration of the energy of the machine during this calibration process. We mentioned very briefly in a previous lecture that in an electron storage ring, one eventually acquires a polarization of the beam, even if you don't inject the electrons in a polarized way. And that has to do with the cross-section for emission of bremsstrahlung photons being dependent on the alignment between the electron spin and the direction of the bending magnetic field. So because of this dependence over time, you see this in a plot from LEP where the level of polarization is creeping up over the scale of tens of minutes as the store goes on. It will naturally acquire this polarization. And it turns out that this polarization level can be interfered with by adding an electron along the line somewhere, or sorry, adding a magnet along the line somewhere, which is giving these electrons a kick on each turn. And you can sort of measure for different frequencies of that kick, how much it enhances or destroys the level of polarization that you see. So you vary the field of this kicking magnet with some frequency, and then you compare that frequency with the precession of the spin polarization axis that you would expect. You know, you have spinning electrons in a magnetic field, you expect that axis of spin to precess around the steering magnetic field. So there's a relation between the revolution frequency, that is the frequency with which the electrons are going around the machine, and the level of effect from this kicking magnet that you apply. And so there's a phenomenon called resonant depolarization, where you basically scan the frequency that this kicking magnet is interfering with the polarization of the beam. And if you achieve a resonant condition, you basically wipe out the polarization for a specific frequency of kicking. And that will tell you in absolute terms what the beam energy is. All the other terms, these are frequencies which you measure. Frequencies are easy to measure directly in an absolute way, as opposed to beam energies. And then these mu terms are the anomalous and the sort of tree level dipole moments of the electron, and the mass of the electron, which is also quite precisely known. So it turns out that you can use this apparatus in order to absolutely calibrate the beam energy at the level of like 10 to the minus 4 or 10 to the minus 5. Lots of interesting physics comes out when you do that. One thing that it turned out that the machine was vulnerable to was tidal forces. So basically, as the moon goes around the Earth, it stretches and deforms the surface of the Earth because of the pull of gravity by the moon. And that slightly sort of rearranges the size and dimensions of the LEP ring in a way that can be tracked with this resonant depolarization technique. So here you see changes in the energy of the machine in MeV over the course of a day as the moon orbits around the Earth. The red line here is the prediction from a model of like the geological forces on the ring. And you see that the measurements of the change in the beam energy during the day match precisely with this model. It's really impressive that they were able to make these measurements at the level of sort of 1 MeV, even though the energy of the beam was like 91 GeV, so almost 100,000 times more. A second influence that they had to suss out, and it was the work of a long time to do, is that there was this sort of alternating periods of noise and calm. So you look at the beam energy, which is measured, and that thing is fluctuating a lot during what's labeled here the noisy period, and then it settles down during the night for this calm period, and then back to a noisy period starting from about 5 in the morning. People spent a long time trying to understand what this effect was. Eventually, it was understood to be the result of current, basically the return current from electric trains in the region. So there's like the train to Paris, and there's trains to other parts of Switzerland running on electric rails. And the current that's like supplied to the train engine, the return path for that current goes to ground. And here the ground is like some complicated arrangement of water and rocks and stuff in the Geneva area. And it turns out that some of this current actually like returns through the plane of the LEP ring, inducing all kinds of currents in the electronics around the ring. And so they had to compensate for the effect of these trains in order to really precisely measure the Z mass. But after a year or so of following up all these effects, you started to see plots like the following. So here's a measurement of that line shape. The central value here with the sort of long dashed line is for 3 generations of neutrinos, and the points are sort of scattered around it, but the best fit line is closer to the n=3 line than to the n=2 or the n=4 line. You can see that in sort of a multi-dimensional plot here, where they contrast the overall cross-section with the total width. And you can see that their best fit values favor a number of light neutrinos equal to 3. This similar analysis is carried out by the other groups. And by the summer of the next year, you have a plot like this, where the data points are really bang on the neutrino =3 hypothesis and very far away from either 2 or 4. This is considered to be a very strong, albeit indirect, proof that the number of generations that have been discovered up till now, 3, is really the number, or at least that if there is a 4th generation, its neutrino must be extremely massive, more than half of the Z width, in order to not be kinematically accessible to the LEP collider. There's a whole program of measurements beyond this, measuring various parameters of the standard model in decays of the Z, since the Z has many different decay modes to all kinds of known particles. It's a very rich laboratory for doing all kinds of studies. And a lot of what we know about the standard model is still coming from these LEP experiments. Not only has it left us the legacy of the tunnel, which houses the LHC, but it's also left us the legacy of a really robust program of precision measurements of the standard model, which still informs a lot of the physics that we try to do and still puts strict constraints on what physics beyond the standard model could look like. With that, I'm out of time for today. So I'm going to stop here. Maybe if there's one burning question, we could try to answer it now.
So, hi, Tate.
Hi.
Can you explain that tidal part for the moon effect? I missed that.
You mean why do the tidal forces affect the energy of the collider?
Yeah.
I think the basic idea is just it's like tidal forces are stretching the physical ring, right? So like there's a differential pull. Like sometimes when the moon is directly overhead, the pull is like orthogonal to the ring direction, but when the moon is off at a 90-degree angle, it's literally like stretching the surface of the Earth. This mostly is like changing the arrangement of the oceans, right? Oceans and water are much more free to move than rocks, but there is even some tidal stress on the rocks. So I believe that the reason for this is just like the physical location of the elements in the ring is shifting a little bit depending on the tidal force from the moon.
Okay. Thank you.
You know, I don't know off the top of my head how much these energy differences correspond to actual physical displacement of things, but you know, the beam is very small and the alignment has to be very good for it to make it around the ring. So I would guess even like very tiny changes on the level of, I don't know how many microns or whatever, actually manifest in a slightly different resonant energy for the accelerator.
Thank you.
Okay, let's stop here for today. In the following lectures, we're going to continue the story of the sort of consolidation of physics experiments. We'll talk more about the Tevatron and its discoveries, as well as the LEP2 program. And we'll also talk about some things which we mentioned today, but didn't have a chance to do in detail, like the time projection chamber. So I hope to see you guys next time. Bye.
Bye-bye. Thank you.
Bye.